Welcome, team. As your lead piping engineer, I'm here to walk you through this explainer on our structural audit. We're going to break down exactly what keeps a 500-degree, high-pressure pipeline from literally tearing itself apart. So let's get right into it. Right off the bat, let's tackle the big question. We don't just guess how sick a pipe should be, right? We engineer it to survive a relentless, continuous battle against some pretty intense physical forces. When you see a massive pipe snaking through a facility, it's not just passively sitting there. It's actually under constant attack from the environment, the boiling fluids rushing inside it, and, well, its own massive weight. Here's our audit itinerary for today. We'll assess daily operating hazards, investigate the dangers of liftoff failures, stress test the system against natural disasters, and finally, verify our digital code compliance.
Okay, Section 1. Surviving daily operating conditions, or the everyday forces attacking our systems.
Let's start with the baseline, which is surviving the standard operating conditions of the plant, well before we even start worrying about catastrophic disasters. Now, our pipes face continuous primary stresses. Think of the immense internal pressure of the fluid and the heavy deadweight of the steel itself. If limits are exceeded here, the pipe will simply burst. No way around it. But we also have to manage secondary stresses, and these are kind of tricky. They happen because a pipe naturally tries to grow and stretch as hot fluids flow through it, but it gets physically trapped by its own supports. That expanding metal has to go somewhere, right? And it forces massive strain into the whole system. And this brings us to a brilliant way to illustrate the danger of thermal fatigue. Think of a metal paperclip. If you bend a paperclip once, it holds up perfectly fine. But if you bend it back and forth constantly, it weakens, fatigues, and snaps. Well, our pipes do the exact same thing when they're forced to cycle between extreme hot and cold operating temperatures. They face what we call moment reversal, which can snap the solid metal over thousands of cycles. So, the absolutely crucial point here is keeping those secondary stresses below the shakedown limit. This is mathematically defined as twice the material's yield stress, or 2SY. Making sure the pipe stays under this threshold means it settles into a safe, elastic range. If we push past it, well, the pipe will suffer permanent plastic deformation. That basically means it physically warps every single time it cools down, pushing it closer and closer to total failure. Moving on to Section 2, the danger of liftoff when supports fail to support. We really need to look closely at what happens when those thermal expansion forces cause the pipe to move in unexpected, highly dangerous ways. In our designs, we frequently use Y+ supports to carry the heavy dead weight of the pipe from underneath. These are what we call single-acting supports, but here's the catch. They're only active when the pipe is physically resting on them. They provide absolutely zero restraint if the pipe decides to move upward. Let's walk through the failure sequence here and see how this builds up. If the pipe heats up and naturally bows upward, it physically lifts off the support. This renders that support completely useless, which means the massive dead weight it was supposed to carry suddenly transfers unevenly to other parts of the line. And that sudden transfer of weight, it can sag or buckle the entire system if we haven't carefully planned for it. All right, Section 3, battling earthquakes and wind, or engineering for occasional loads. With our daily operations locked down, our audit has to account for occasional loads. We're talking about the sudden, rare, but incredibly violent shocks from environmental disasters. For outdoor piping, we actually calculate wind as dynamic kinetic energy pushing against the pipe. We rely on extensive meteorological data, like the fastest mile wind contours mapped out across different regions, to figure out the maximum aerodynamic pressure our support structures must withstand. We literally have to calculate the aerodynamic drag on our steel tubes so they don't just blow over like dominoes in a storm. Now, while wind requires those aerodynamic drag calculations, earthquakes require specialized, dynamic hardware. We use devices called snubbers. These are really cool. They allow for slow thermal movement as the pipe heats up, but they instantly lock up during the violent shaking of an earthquake. It's exactly like how a car seatbelt functions in a crash. You know what's really fascinating here? Our standardized codes actually don't require us to combine these two extreme occasional loads simultaneously in our calculations. The mathematical probability of a record-breaking hurricane and a catastrophic earthquake happening in the exact same second is so phenomenally low that the codes allow us to test for them independently. And hey, if you think above ground is tough, buried pipes face their own unique seismic nightmare. The shifting earth transfers extreme strain directly into the trapped pipe. Because the continuous soil restraint is fighting against the pipe's natural movement,
all that energy has nowhere to go. This can lead to a phenomenon we call column buckling, where the sheer axial stress literally pops the pipeline completely out of the ground at mid-span.
Section 4. Verifying code compliance, which is our digital testing ground.
As your lead engineer, I definitely don't wait for a physical pipe to break to find out if my design works. We verify everything digitally first to ensure total safety. We never, ever rely on guesswork. We strictly adhere to ASME rulebooks, like B31.3 for process plants. These highly regulated codes dictate the mandatory formulas, the allowable stresses, and the absolutely uncompromising safety factors that all our designs must meet. To guarantee this, we use advanced software, like Caesar II, to run the complex code equations. Take equation B439, for example. The software runs these exact calculations to prove that our anticipated stresses stay strictly below the allowable stress limit for that specific metal, even at its absolute maximum operating temperature.
Our digital models are exhaustive. The software takes in all those sustained, expansion, and occasional loads, and then it actually multiplies the stress at known weak points using stress intensification factors, or SIFs. This guarantees two things: structural integrity so the pipe won't burst, and operational integrity so it won't warp and leak at the flanges.
So, we can model every stress factor perfectly in the digital world. We can account for the heats, the pressure, the wind, and the earthquakes. But, as we all know, nature always finds new ways to test our limits. Our job is to build systems that survive no matter what gets thrown at them. So, I'll leave you with this one thought. Are you ready for the next audit?